I'm happy to introduce Dr. Alexa Halford, who is the lab chief of the Ionosphere, Thermosphere, Mesosphere lab at NASA Goddard. And she is also the deputy project scientist for this new mission that she will be telling us all about. And this is kind of based on, I think, her AGU talk, which was a while ago, but had some really great analogies about global auroral imaging. And that's something I know is of interest for folks in the Zoom room here and myself. And we're really honored to have proposed Aurorasaurus as part of this so that there can be hopefully, fingers crossed, if this is funded, that it could be a way for people to participate all over the globe alongside a NASA mission with Aurora citizen science. So I will turn it over to you, Alexa. Thank you.
Yeah, thanks. And thanks for having me. Let me see if I can share my screen. Maybe. We should have tried this beforehand. It says that it should allow it, but it's not seeming to allow it.
Seems like it would allow it for me, but I don't know if I have some special permission. I don't think we
It's
normally.
telling me I have to quit and reopen, so I will be right back. I'm sorry
Okay,
for this.
that's all right. Let's say NASA Zoom connection probably issue.
So Liz, when she comes back on, I'm just for the sake of clipping the for the sake of clipping the video, I'm just gonna have you reintroduce her one more time.
Restart.
Or we could do it that way.
Either way, I don't know. I'm not
Okay.
a video maker, so
Does not matter.
yeah.
Oh, here come the clouds in the wind. We're getting the remnants of the hurricane that wasn't coming through. Yeah. Oh, here comes Alexa. You should be good.
Welcome.
Hey, welcome back. You're muted.
Okay, we'll get all the bugs out of the way and then the rest of the presentation will go well, right? Yeah.
Awesome.
So
Thank you.
here, I figured I'd give a little bit of an introduction of the ITM lab itself, just because I think it's always kind of nice to know what your friendly government scientist is doing for you. And so, as Liz said, I am the lab chief for the Ionosphere, Thermosphere, Mesosphere lab at NASA Goddard. And our mission really is sharing and expanding our understanding of connections between humans, our atmosphere, and space. And that includes then the aurora and the auroral dynamics, along with some of the space weather impacts like communication errors and GPS errors and precision farming that a lot of people use, or even understanding the radiation at aviation altitudes and things like that. So we do a lot of different types of work that are relevant to most people at least some of the time. So who are we? We're specialists and generalists. We're physicists, engineers, and even historians, which you know, Laura, observationalists, experimentalists, model developers, and then we study a lot of the different sections between the atmosphere, the ionosphere, and the magnetosphere. So with that, this is kind of the region of space we look at, anywhere from about 50 kilometers, sometimes a little bit further down, on upwards of 400 miles and even further out. And that definitely then has the part of the ionosphere and atmosphere that the aurora live in. And as you can see on the right-hand side, there's some of the different space weather impacts that this region then holds, whether that's like I mentioned, the precision farming, the GPS navigation systems, drilling and oil production, as well as radiation, aviation, and astronaut altitudes and beyond. As I go through, if you have questions, feel free to interrupt, or we can wait until the end to ask questions as well. Either way works for me. But one of the things that I thought I'd start off with before we got into the mission we hope will launch is a mission that launched a few years ago. So Vincent was part of this one too. This is the rockets and ground measurements that we used to study the aurora. And the mission I'm going to tell you a little bit about is the LAMP rocket mission, which you can see the picture of it there. So it was a two-stage rocket. So that's where you get to see kind of the first big line and then a second one. That second one is when the second rocket really took off. And it was going to study the pulsating aurora. So after you have the beautiful rivers and everything like that, you start kind of getting this pulsating system, which you can sort of see happening over here. So this is a movie from Venati. I believe it might keep going. But one of the cool things about this rocket was that not only did we have all these different ground stations where you could see the aurora, but we had a camera on the rocket itself, which you see on the left-hand side spinning. And after it got to about, I think it was 200 kilometers, it despun. So it actually went in the opposite direction as the rocket was spinning in order to make sure that we could get pictures of the aurora looking down from above. Now, one of the things that is really, really obvious that we kind of knew about, but I don't think we realized quite how much it would impact it, is that it turns out snow is reflective. And so you can tell that the image on the left is maybe not quite as clear as the image on the right. And that's because not only are we seeing the aurora and the movement of the aurora there, but we're also seeing the reflection from the ground of the aurora, which I don't know, I think is kind of fun. Now, we can tie that to measurements of particles that we actually saw in the rocket, which is up above. But what's really fun here is we're going to see 3 different images. So we're going to see the 3 ground cameras that are all looking up. And then we're going to see, I believe, this one. And we'll notice right when I get to it, if I remember correctly, the order of these, or if I got it mixed up. One of them is just going to be showing kind of a square patch from inside here of what the rocket's field of view should look like. And then in the other one, we're going to see the actual image of the rocket. So you can see how well they match up. So there, that was the rocket launch in the camera. And then this is where, yep, we've got the rocket square, what it's seeing as it's flying overhead. And then this is the image that is seen from the rocket. And what's really kind of cool is you can see how we can now match up the different pulsations and actual dynamics of the aurora from both the ground looking up and from the rocket looking down. And then we can tie some of that into the different particles that we're capturing on the rocket itself. So we can get a better understanding of what energy of particles are associated with the different dynamics of the aurora itself. And then, of course, trees get in the way, because trees always get in the way. And then it goes down. Now, what's really neat is because we have all these different views, and I know you guys have been a part of some of these efforts as well, not with the LAMP rocket, but with other events that have happened, is that we can start actually triangulating at what altitude is the aurora happening at. And that's really nice because we think we understand what height those particles are going to be interacting with the atmosphere at. And this is a way to kind of test it. So here's the same kind of image. One is not going to have much going on, but the other one is actually going to show the colors here are going to be associated with dots that come on the screen that are where the different auroral features are seen. And it's going to tell you what height best matches where that feature seems to be when you triangulate the different images from the 3 different ground-based cameras. And so you can see there it's all coming in. It's starting off pretty high, a few low bits, and it starts kind of coming down in altitude a little bit when we have all these wonderful dynamics. See a bit more green and blue in there. And then as it starts going into that pulsating aurora, it really kind of settles in at that about 100-kilometer altitude, maybe a little bit lower, maybe a little bit higher, depending on the individual kind of bit and the individual feature. And so this is really exciting and interesting because it's giving us that really small scale, fast time scale sort of processes that can help inform us what is happening in the magnetosphere that's then driving these different auroral dynamics, which is really kind of fun. But we're going to actually go from there to step back to give us a much broader global view. So it's really fun to see those individual dynamics, but how widespread is that? How big is it? And then really how asymmetric, how similar is the northern hemisphere to the southern hemisphere? And so that lamp launched in, I believe it was March of 2022, March 5th of 2022. And as Liz said, we're really hoping to kind of propose this new idea. And so to start, I always like to kind of zoom in. Lamp was kind of like this image. It was really close up. And so what do we think we're seeing? Is it like a moon, a desert, a skin from some animal? As we zoom out, we might see that, oh, there's actually an eye, like some of those nice auroral kind of swirls that we can get. And we might start thinking that some of these dynamics are actually associated with how muscles are formed and where the blood flow is going. But if we're only looking at one side, we might think that it all looks like the front side of an elephant. And so we want to know, is there symmetry in the system? Often there's symmetry in the Earth. We know that it has a nice magnetic field. It looks pretty symmetric. We think we know what one side looks like, so the other side probably looks like the same thing. We know that's maybe not quite true, though. It would be hilarious. This is something you definitely would see from Dr. Seuss in one of his books. But we kind of know what other large four-legged animals might look like. We might not have ever seen an elephant before in our lives, and so maybe we think it's something kind of like a horse. And I have to say, I'm very proud of my PowerPoint processing here. I am not an artist, and you can see why I maybe never went into an art profession. But I think, this kind of gets that idea across that when we're only looking at one half of something, we know we're probably getting a bunch of it wrong. When we're trying to model the Earth's magnetosphere from a perspective from, with computers, we're having to pick grid sizes that might not be the right size. We're having to match systems that maybe aren't quite really all put together properly. And so we're probably looking at something that's like this combination of a horse and an elephant in many of our models. And it'd really be nice if we could actually look at both sides at the same time and see how similar they really are and how it all kind of fits together to get the real accurate picture of what the aurora is doing in both the northern and southern hemisphere. So it turns out, though, that this is really, really difficult because space is big, like really, really big, like bigger than an elephant for sure. So we often have to make a choice at what and how we're going to look at it. And that's kind of where, like with LAMP, we made the choice to look at something really small and manageable. But we want to try to not have to do that. So we've taken this idea that we need something really new. And this is something that's never been done really at Earth, or not in a intentional way. And so we want to have two auroral imagers. And we've flown auroral imagers before. We've actually flown them for most of my lifetime. The first one really came from 1981, which was just after I was born. And we've had auroral imagers then on missions from DE1, Polar, and Image. But these were Polar and Image were global views. DE didn't always give us a full global view. Time UV had not an imager, but 1D slits. And really the last time that we had this view of just even one hemisphere's auroral oval was in 2005. So it's been almost 20 years since we've seen the full auroral oval. And we've tried to do those close-up views and get better and better at that. We can do some of it sort of with ground arrays and really large ground arrays. This is from the Canadian imagery. And you can see that you start getting the picture, right? You kind of understand how something can be connected on this kind of continental level. However, it's really difficult to put imagers on land, let alone in some of the other different countries where we'd want to get images from as well. And even just getting them down in Antarctica is difficult because you have lack of power and consistency of power, and capabilities to kind of keep things running down there. And so with Max, we're hoping to have 2 imagers that are going to be flying over the poles in circular orbits, and so that we can get really long-lived times kind of sitting there and viewing each auroral oval. And that will give us the ability to see more of those meso and you have macro, micro, and meso. So meso and, I'm dyslexic. I'm going to get these all mixed up. Meso and macro scales. So you can get those kind of larger images of really seeing how the energy is flowing through the magnetosphere and into the ionosphere and atmosphere with the auroral signatures going through there. So our phase,
Alexa.
yep.
Oh, sorry to interrupt you.
Sorry,
I just
no,
wanted to add, like,
Yeah.
mesoscale kind of, people are familiar already, I think, with mesoscale features that we talk about with the Aurora, but like
Yeah.
omega bands and
Yeah.
various things like that that are pretty big. And then like the micro scale features are really much more what the rocket was looking at, because the
Absolutely.
rocket's moving so slow and it's like sampling one individual patch and then moving on to the next one. And it's interesting. Yeah, I just wanted to add that. So
Absolutely. The micro scale with LAMP was very much kind of on the tens of meters or even sort of smaller sometimes kind of scale, versus here we're looking at kilometers and larger kind of sort of scales.
and citizen scientists kind of imaging both micro and meso scales, whereas like from an imager in space, you really get those
Yeah,
global and meso scales. So
absolutely. And you need all of them, right? You need all of them from multiple angles and multiple viewpoints to really understand the whole system. So we are data starved, and so all the data we can get is valuable, right? And I think that's always an important thing to think about. So the first phase, if we get to go, would be launching sometime close to 2030. Exact dates, are never great to give because things change with timescales or with just events that happen. But the first phase that we're going to do would be to have, if we get selected, would be to have the 180-degree orbits. So we'd effectively get full coverage for quite a long time, and we could see how changes are different between the northern and southern hemisphere, and that's really important. So the Earth's field is, or the Earth's axis of rotation is tilted, and then on top of that, the magnetic field's axis is tilted, but not just tilted, it's tilted and kind of bent. And so there's asymmetries all in that system already. So we wouldn't expect them to be exactly the same, but how different are they, I think is really a big question up for grabs. There's been some work in that, but not consistently. It's always been like case studies when you happen to have like polar and image both looking at different hemispheres, and that happened only a handful of times. So this should be really exciting. And it's the first time we'd be able to do that with identical imagers. So polar and image had different instrumentation on it. So even though we think we can kind of understand how to go between them, there's always then that little bit of translation you have to do between the two different types of data sets. And here we wouldn't have to do that. Here we would know exactly what we're kind of looking at. The second phase then would be where we'd have the two satellites in 90-degree kind of separation from there. And that means that we could still see one pole much more for a longer period of time. And then we would always see one, at least part of the aurora in either hemisphere for a 24-hour period. And that's really nice too, because then you can see kind of that consistent what's happening within the magnetosphere. And so that large scale kind of questions that we're looking at is how is energy moving throughout the system? How is it going from that day side where the solar wind kind of helps open up those field lines, pass energy into the tail, and then ultimately come back through the magnetosphere and then down into the aurora. And this should be really interesting. So the OCFLB, I thought I caught all of the acronyms. I did not in this presentation. That's the open closed field line boundary. And so we often can estimate that based off of the auroral oval and the size of the auroral oval there, which is one of the reasons why you want to be able to capture the whole thing, is you want to be able to see how big is it getting, and it's often somewhat asymmetric itself. So you don't want to have to guess too much if you don't have to. So that's really kind of fun. And then we want to be able to look at those mesoscale energy features where we can then trace how they're moving in the atmosphere, which then kind of gives us an idea of what's happening out in the magnetosphere and in the tail. So these two images up here are from global magnetohydrodynamic movies of what we think is going on. And so we'll be able to take the images that we see down in the atmosphere in either hemisphere and kind of trace them back out into the tail and see how well they match the oval there, or match the model there, which should be really, really kind of fun. Now, you might ask, how much better do we expect to get our images from past missions? So here we have DE1, which was from 1981 to 1999, and you can see its field of view in the camera, what it looks like. Now, Polar was a bit better. So this is the same, like if you took the same picture with Polar's instrument instead of DE1, this is what you would get. Image was yet another advancement from there. And then this is what we expect we would be able to see with Max. And so you can see that we're getting much, much more detail, much finer scale detail in what we think the processes would be, and just an overall better image. But the real key thing is that we'd actually get two of those images, one from either hemisphere, which would be amazing and cool. And this would provide measurements that would need for the next level of predictions. So once we're able to get those kinds of images, we can both train on the data for machine learning models, as well as hopefully improve the physics-based models as well. So that next time when you're wondering, is the auroral oval going to come down to my latitude, we might do a little bit better. Although you never know, right? You always want to go out and see anyway. So the Max team is quite large. It always does take a community to do science, as you all know very well. The PI is Mike Lamone from the University of Michigan, and the project scientist is Aaron Ridley, and the deputy PI is Dan Welling. And then, as Liz said, I'm the deputy project scientist, and I'm at NASA Goddard, and we have a number of other scientists from NASA Goddard there, as well as the instrument coming from University of California, Berkeley by Tom Immel, who actually has done lots of work with previous imagers as well. And then we have, Howard Community College, Pepperdine U, who will both be really helping us bring in kind of the students into the project as well. And then we have the collaborators at the Aerospace Corporation, the University of Colorado, and the University of Calgary, who will really help bring some of the ground-based stuff as well. And then we have project management team too. So this is truly like a full-on national effort, as well as an international effort with the Canadians' involvement as well. And just as an acknowledgement that we've been doing a lot of this work on the research grant from NASA and NSF and this MEX Phase A contract. And while Goddard itself does not have a land acknowledgement, the University of Michigan does. And it's really important for us as the team to acknowledge not just their land acknowledgement, but others as well. So, they have theirs there. But hopefully this will all lead to us in the next decade or so being able to go see the aurora. And we've never had a mission like this before. And we're really hopeful that if we get selected, we'll be able to have you guys involved so that we can get not just the pictures from the the two satellites, but then as Liz said, we can really start getting some of the micro and meso scale pictures from the citizen science groups coming in as well to really provide that extra layer of data, that extra set of eyes and perspective, literally that different perspective, so that we can get out information like the height information of the aurora, as we did with the LAMP mission. So hopefully, fingers crossed, all goes well. It was submitted last week. And now we just have to hang tight and wait, which is, I think, almost the worst part. So, hopefully you guys have questions.
Yes, thank you, Alexa.